introduce our speaker, but first I want to say that I don't remember who is our actually. Sorry, I didn't look to see who are our sponsors, but thanks to our sponsors. But I also want to say thanks to the students and to the professors that they keep on coming and actually supporting this. This has been, I don't know if you know, the control seminar has been around for as long as I remember it, and I've been here like almost 35 years now. So it was before that, so it's like close to like 45 years. I don't know if you know that. And it happens, huh?
You claimed it's here since 70s.
Oh, there you go. But I can also say only what I know and I remember. So 35 years I've been here every Friday. No, I haven't been here every Friday at 3:30, to be honest. I've been slacking lately. And now I'm buying time so that you can get more coffee and more cookies. Okay, anyway, so thanks for coming. I am also privileged today to say that Bryan is my student, my PhD former student, yay. And he came here actually with a math and a mechanical engineering background, and he did his 5 years PhD, and then he, on one subject and then in another subject. Now he's going to talk us about the third subject.
Okay.
And he just got awarded 40 under 40 at the whole Knoxville, the city of Knoxville. He keeps on getting awards, so I think it's going to be fun.
Okay. Thank you, Anna. Yeah. Thanks. Thanks for the warm welcome. It's very nice to be here. A lot of memories, a lot of good times as always. So my talk is going to be about the research that we're doing at Oak Ridge National Lab regarding controls and automation applied to construction of buildings. So it's quite an interesting topic. Yes, Anna mentioned, I have started doing this for the last 2 years. And you will see how I was able to sneak in some controls here and there. So hopefully you enjoy. But first, I'm going to start with acknowledgements. So within RNL, we have formed this advanced construction laboratory. We have Diana Hon, who is our group leader, and she's the expert on building science and advanced manufacturing. She's basically the one that understands very well the problems that the building sector faces in the US. We have Nolan Hayes and Menja Tan, who work in construction processes, advanced sensors, and advanced tools. You can see Nolan using a total station that is a super accurate way of measuring things in buildings, distances, basically. You have me and Yifan Yu. We are the controls and robotics team. So we are the ones that are always on the whiteboard writing math and pulling our hairs out. And then we recently hired 2 postmasters who are our computer science and artificial intelligence team. You can see them. They were recently participated in a hackathon at RNL, where we were trying to drop some of our deep learning algorithms into Frontier, that is the fastest supercomputer in the world. So they are there hacking and having fun. So it's been great. So let's start with some motivation. So So the main motivation is what is happening right now with the residential buildings area in the US. So you can see here that most of the buildings have been built before 1980s, where the building codes started to be in effect in the US. So this means that these houses are very inefficient. And these amount to more or less 64 million houses. And they're inefficient because they have low or no thermal insulation. So basically, all the heat that is produced in the home to warm up escapes through the walls or through the roof. Or in the winter, in the summer, a lot of heat gets inside of it. So you have to use your cooling capacity for that. And that makes them 25% less efficient compared to modern houses. Because of this waste of energy, a lot of the carbon dioxide emissions that is produced within the building so 70% of this, the envelope is responsible. And the envelope is basically the walls, the roof, everything that involves the living space. So there's a lot of, basically this says that there is a lot of heat wasted. Another important thing is that out of the 64 million houses, 50 million of them belong to low-income households. So that means that they have to use a lot of their income money to pay energy bills. And on average, they have to pay around $273 per year, in addition to what people who have more efficient houses have to pay. So this is a lot of burden for low-income households. So the Department of Energy now has this big project and this big investment on retrofitting these old buildings. So we want to bring these old buildings to code, make them more efficient. And there are basically three main ways of doing it. You can retrofit the building equipment. So that is your HVAC, for example, refrigerator, lining, things like that. The fenestration, which are the windows. So nowadays there are very high-tech windows that you can use where you lose very few heat through them. And the last part, which is the one that I focus on, is the building envelope. So walls, attic, and crawl space if the house has crawl space. So now retrofit is not a new thing. Things have been happening lately. The problem is that they are happening too slow. So the blue line here shows what happens if the current retrofit rate, which is 2% every year, continues at the current pace. And DOE has this super aggressive goal of decarbonizing everything by 2050. So clearly we won't hit it. So we have to accelerate the rate at which we retrofit. And that means that we have to increase this fivefold. So if we retrofit 10% of houses each year, we will be able to make this goal. In order to communicate this, Department of Energy has written two main pieces of information. One is the National Blueprint for Building Sector Decarbonization that basically elaborates all the issues that exist right now and all the potentials for researchers like us to tackle and to help this sector. And the other thing is super important. One of the energy airshots, which are these very ambitious goals that the Department of Energy has, one of them being hydrogen or solar. Now, affordable home is one of them. So there is a lot of interest on right now bring this house up to code and make them more energy efficient. So that is the motivation. That's why we're doing this. So what is the challenge? One of the main things is that the building sector has been typical to resist automation. So this is a comparison of different sectors. You can see the agriculture. If you compare what happened in 1940 to 2016, agriculture has grown by a factor of over 1,000, manufacturing by a factor of over 700, and building construction by a factor of 6. So this is quite embarrassing. You can see here the differences. The only difference here is that now we wear hard hats, which is good for safety. But then, very manual, very rustic. They have not been, there is a lot of inertia to automate in this sector, basically. So that is a big challenge. Another important challenge is that right now we're facing a lack of skilled labor. There is a labor shortage. Latest numbers that I heard were about 500,000 people that we're lacking to keep up with the demand of housing. So it's a severe problem. So with all of these plans that we are going to present, the potential for scaling this number is to at least bring it up to a factor of 100 by 2050. So again, super ambitious goals. So the innovative solution now for this actually comes from Europe, from a program called Energy Sprung, which has been quite successful, quite popular. They can be found in the Netherlands, in Germany, in France, in the UK. And basically what they're trying to do is to retrofit buildings with the minimum amount of these disruptants to the occupants. So that's an example of a building that you want to retrofit. So what you do is you do a survey and you determine the dimensions of the different components. So you measure where the windows are, where the doors are, what are the dimensions and all of that. You create an architectural drawing of it. Then you design these panels that can be prefabricated. So this means that these panels are made in a very tight manufacturing conditions. They are super high tech. And then you ship these to the construction site, and then you install them. Then you put, it's like a Lego block set, you cover the building, and now the building is up to code. Super popular, but comes with a lot of buts. There is a lot of problems here. So let's see. This is a video from Estonia, from one of our friends from there. And this is an example of an older building being retrofitted. So in this, the term that you're gonna hear a lot is overclad panel installation. Overclad meaning that it's over the existing wall. And let me play it. So you will see that this is very manual. So it requires a lot of different machinery. They have to remove certain components. Then we bring the panels. They start installing the panels here and here. These are the prefabricated overclad panels that they install. They also have to deal with the roof, but you see people everywhere. There are people climbing the roofs, people installing the panels. So it's still very manual. There is no true feedback, so you don't really know if the panels are installed correctly. There might be some air gaps, or there might be some overlap between panels. So that means that you have to then rework and cut some pieces of the panel, which amounts to a loss of time and money. So then our research focus is to automate this process by closing the loop. So I'm gonna walk you through what is the control loop for how the control loop looks like. So you have the building that you want to retrofit, and you have the panel that you want to install. And the first thing that you do is you need to create a digital twin of the building. Basically, this is a geometrical twin where you have all the architectural designs, where things are, because you need to know your target position. And we are doing this using LiDAR scanners, super accurate LiDAR scanners. Now that you know where things should be, you need to know where things are. So now you need to track how these prefabricated panels move on space. We are using laser trackers for that. IMUs, and we want to introduce cameras as well. So basically this tracks position, orientation, linear velocity, and angular velocity. So then you know basically where you want your target, you know where you're at in real time, so then you can calculate the error. So this is the key part of the feedback loop. So once you have that, you could provide this feedback to a human installation crew, which is one of, I'll discuss that later on. But you could also provide this feedback to a robot. And that is the last part, is how you can use this to enhance robot installation, to make installation faster, less dangerous because you don't have crews moving along this, installing these panels, and also more accurate. So I'm gonna talk about each of these components separately. So you can see how the dynamics and controls kind of like come here, and the machine learning kind of like comes in that part. So I'll show you how we generate digital twins of buildings. So in the first part, the problem is that you need to get the accurate as-built dimensions. And I really want you after this to go to your house and take a square ruler and try to find right angles. There are no right angles in houses. Windows, all of them are crooked. Walls are probably not plumb. So you have to face all of these issues when retrofitting this. So you have to capture every single crookedness in order to design the panels appropriately. Right now, with some commercial methods, you can get accuracies of around 13 millimeters, which is half an inch. But we really want to achieve an accuracy of 3 millimeters, because the more accurate you are, the tighter you can retrofit the building. So then the tighter you can keep the heat inside. It's all about efficiency. So you don't want to have air gaps. So that is our target. So we developed this algorithm that is the automatic point cloud building envelope segmentation. We call it AutoCubes. And basically what it does is it takes this point cloud. So this is, we use LiDAR to scan the building from all the different facades. We put all the point clouds together. And then we have this super nice, highly detailed twin of the building. But we do not need to know all of these details. So what we really need is to extract the dimensions of each component, which you are simplifying from around 32 million points to around 300, which are the really important points that you need for designing these panels. And the idea is that we are using several machine learning algorithms to do this, instead of using, instead of a human trying to do this segmentation task. We have had excellent results, especially on time reduction. There are companies that can do this process manually, and they will tell you, yeah, we can do it, but give us 2 days. There are some semi-automatic methods that maybe can do it in 4 hours, but we can do it in 12 minutes. So this is a significant reduction in time. But the main gain is really the accuracy, because now you have the true accuracy of the LiDAR machine to detect the dimensions, rather than the human subjective perception of, oh, this is the dimension of the window, or this is the dimension of the door, which once you drill down to the details, is very subjective how we measure things. So this is quite interesting to have this part. So let's talk about the machine learning part. There are 2 main sensors that are used for segmentation: the camera and the LiDAR. If you are into machine learning, you might have seen that the camera works very well, because the pixelation basically gives you a matrix, and you can do a lot of nice matrix operations like convolution and things like that. But you lose accuracy, and we are all about accuracy. So the LiDAR can give you a super nice, fine, accurate point cloud, but now you're losing really order, right? The pixels in a camera are an order array. These, if I give you an array and I shuffle the elements, it produces the same thing. So there is not that nice structure. It gives you more detail, but it loses that structure that cameras have. So precisely for that reason, supervised learning has been used mostly with cameras, or even if you have sensor fusion, the segmentation really happens in the camera. So there has been a couple of studies that use cameras for segmenting buildings, but again, these are not automated. There are promising developments on deep learning where you can do segmentation of point clouds, but these segmentations occur with everyday objects like chairs, tables, things that people just scan, or autonomous vehicles think about. So you can segment the road from the trees, but there is no really data set on building envelope. So we cannot train a neural network if we do not have labeled data. So that is the problem that we face. That's why we went for a supervised learning. And the challenge here is that supervised learning, you have just a network that does everything for you, while unsupervised learning, you have to be more systematic. You have to go step by step of trying to break the problem into simple components, and then break that component into more simple components, and then solve the problem. So I won't give you all the details, but I will give you the key idea of why this thing works. So this is a picture of a typical brick cladding residential building that I took. And the cool thing about all of this is that we can observe a lot of differences between the wall and the window, but geometrically there is a very clear difference in which the window most of the time is recessed with respect to the wall. So if you picture the LiDAR here, the LiDAR is shooting lasers in all of these surfaces, and the LiDAR is going to pick up this wall as a super steep peak in the distribution of points. So if you take your point cloud and you project into the depth axis, so this is a transversal cut, and I project that point cloud, you can use a histogram to identify where the wall is, or most elegantly, you can use non-parametric approximations to approximate this distribution. And the nice thing about non-parametric approximations is that they are differentiable. So then you can differentiate this distribution and find out where the peaks and where the valleys are. So obviously this peak is obvious because here is where the wall is. But the peak that is not obvious is this little peak here where the windows are. So this is, if you project these points down, you're gonna have a little peak here and then a big peak here. And we can capture these peaks surprisingly well. And you can see how then it's broken into 3 parts. The main part, which is the wall, the interior part, which has the window. It has other things too, but the window is here. And then the exterior part where you can see, for example, the window sill or the eave. So you can break the wall into that part. So that's kind of neat. And then, once you have this, you can identify this as being the most dense cloud, and then you can use, let me go to the next one. So yeah, so you can then use DB scan and just say, okay, I want to find the location where the most density of points are. You find them, and after that, you simply solve the bounding box problem, which now there are algorithms that can solve this very efficiently. And then you just use a bounding box problem to find where the things are. Of course, you're constraining this as a rectangle, or as a box, but it works well enough in our experience. So that is how you can generate this digital twin from the data and just extract the parts that you want. So the next part is, okay, you know where things need to be. How do you know where things are? So we call this the real-time panel position and orientation evaluation. You can see in this picture a traditional way of installing panels. You have your prefabricated panel here. There is a hole where the panel should go. There is a crane that has a crane operator, and then there is the installation crew. So the installation crew, they have walkie-talkies, and they're like, okay, to the person who is operating the crane, like, okay, move it a little bit to the left. Okay, now move it to the right. Okay, I think this is good. Just drop the panel. Okay, yeah, seems good. Okay, move to the next panel. So there is not really a good way of measuring how well the installation is happening. There is a lot of eyeballing and hand waving, and that gives you to a certain level of accuracy, but not the one that we need. So how we done this? So we created this digital tool that we call the real-time evaluator that actually recently won an R&D 100. So we're very proud about this. And the whole point of it is to, once you have the digital twin, you can track where the panel is, and then you can compute the error, and you can communicate this error to the crew. So this is your feedback mechanism. Right now is human in the loop. So you give the feedback to the human to say, you are 3 millimeters off, move it here. You are 3 millimeters to the front, push it back. So you can communicate with the crane operator in a very precise way, and you can see in real time how the error reduces. We have done this obviously at the lab scale, but also in the big scale, and it actually works quite nicely. So what do we need from here? We need a laser tracker, most recently seen in the Paris Olympics. I don't know if you've paid attention. I am into like field type of events, and they are so precise that they use this to measure shot puts and javelin throws and discus throws. So you might have seen these guys standing there. That's what they use to actually measure the distances of the throws. Quite accurate equipment. To track where the panel is, we install these prisms in the panel. And then basically this is a robotic tracker. So the tracker locks onto the prism, and then it can follow the prism super, super accurately. But that really only gives you position. At the beginning, we started playing with 3 of them, because if you have 3 prisms, you can basically scan each prism, and you have a plane which gives you the orientation. But it really, it takes too long to do that. So we are right now playing with IMUs to give us, and this is nice because this gives us orientation and angular velocity. This one gives us position. So these are the current feedback sensors that we're using. So this is how it looks in our experimental setup. We have the total station that could be up to 100 yards away, super accurate, tracking the prism. This works with a Bluetooth antenna talking to the computer, and then the IMU, we have a wireless IMU because wired IMU really doesn't work for this application. It has to be wireless, talking to the computer. And these 2 pieces are in some sort of a clipping mechanism that you clip to the panel, because you have to be able to remove it. You cannot just leave it there. This little prism here is around $1,000, so you don't want to just sacrifice $1,000 for the sake of efficiency. So you have to be able to recover them. So there we have developed these systems that you can attach to the panels and detach to the panels in order to keep track of where they are. So this is our experimental setup down there in Tennessee in Oak Ridge National Lab. So you can see Nolan here. He's about to install this panel. So he has already installed these 4. The connections are already in place. This whole digital tool can also help you install the connections. But you can see the cable here. So there is like a crane that he's going to use to install. And this is our interface that can be projected in a handheld device. And you can track the error in position and the error in orientation. So if I let it play, you will see how the numbers, the position numbers, they update in real time. The orientation numbers don't, because we don't have the IMU here yet. So we have 3 lasers, and you will see how long it takes to update the orientation. But the position can give you quite close, but then Nolan has to go back to the computer and tell the robotic station, now look for the 3 prisms and give me the orientation numbers. So now the orientation numbers update, and then you can just focus on the position, and all becomes green, means that you're good. So as I mentioned, we have also tested this in larger scale experiments, which have been working quite good. And the ultimate deployment of this is a project that we have with the Knoxville Community Development Corporation, where we are going to help retrofit 2 low-income housing. So you can see here how it looks. They were built in the 1940s when Oak Ridge basically was built for the war, if you know the history of World War II. And this is a render that the architect provided. And you can see how the house looks wider because the panels are installed on top of them. They're overclad. We had a nice visit from Secretary Granholm, former governor of Michigan, now Secretary of Energy, that came down and visited us. So she was quite happy about our partnership with Knoxville and the low-income communities there. So, okay, the last part, I guess this is the more fun part for you, where I can actually show you equations. So in this case is, okay, where things should be, that's from the digital twin, where things are that are coming from all these sensors I was talking about. So what do you do about it now? And you can provide these commands, these control commands to the human in the loop way, but you can also go fully autonomous. So this is a rendering of a cable-driven parallel robot that we have been conceiving. So basically, the idea is you do not want to have a crane because cranes are very bulky, and in densely populated areas, they are not super popular. But you can have a robot that basically lives in an enclosure that could be as big as the building itself, doesn't have to be taller. And then you have a bunch of cables coming from the panel, and then depending on how you pull the panel, the cables, you can adjust the position and orientation of the panel. So this is a prototype we're building right now at RNL. So this is a 1/3 scale of a 3-story building. So 10 feet high, 9 feet wide. So it's quite big, but it's still it's a toy model, right? It's not a building size thing. So we just finished with that. We have a bunch of the electrical and control components there. We're right now assembling the actuator train, and then we're going to connect all the cables to a panel, and then we're going to start controlling this. So whenever we were brainstorming and trying to figure this thing out, we thought we were super clever, and then we started looking, for literature review and said, okay, what other people are doing? And surprise, surprise, Europe is once more ahead of us. So this is a project that is called Hephaestus that was done in between Spain and Germany, and among other institutions, but those 2 were the biggest one. And it's a cable-driven parallel robot that can install glass panels, not necessarily overclad insulation panels, but it can install glass panels. So they have all the cables, all the equipment, and they have actually demonstrated how you can operate this massive thing in order to install large-scale products. The problem is that this robot operates in an open loop way. So it doesn't reject disturbances. And I was lucky enough to talk to the Hephaestus team, and they told me, I don't know, we calculated trajectory, we knew the force that we needed, and then we let the robot go. And then at the end of the day, it didn't arrive to the position we wanted. We were 2 inches off. And the reason is because they had disturbances along the way. If you have a high wind hitting on one of your panels, the robot is going to move. And because you don't have feedback, you cannot accommodate for the error. So we think we can do it better, but we'll see. Maybe if I get to come back, I can get you better results a couple of years down the line. So you can see here how we have modeled this type of robots. So it's all rigid body movement. So you have Newton's translation equation, Euler's rotation equations. We have a nice set of states, which is basically position, orientation, linear velocity, angular velocity. And then the control command are the tensile forces in each cable. So in this case, we have 8 cables because we have, you can think about this of a cuboid. So each vertex is connected to the frame of the robot. So we need 8 cables for that. So this is a nice nonlinear system with these very important constraints on the force. You have a maximum force, obviously, because we don't want to break the cables. That will be very bad. So you are constrained. You have an upper bound for that, but you also have a lower bound for cable sagging because you do not want that. The moment that you have a sagging cable, you lose control authority because you cannot have a tensile force on it. So we developed this model. We started with the simulations. First of all, one of the many lessons that we learned is that the moment that you want to design these cable-driven parallel robots, you have to decide how you connect the panel to the robot frame. And if you have 8 cables, you have 8 factorial combinations. So we had to basically, run simulations and evaluate what was the best combination. And we ended up with 4 very promising models at the end of the day. The second lesson that we learned is that friction actually is very important. And I'll show you why. This is a simulation of the model I showed you before. And you can see the blue line is the target trajectory that we wanted. And the black one is the simulated trajectory. So super oscillatory. We really didn't understand what was going on. We were looking at this and like, this doesn't make sense. That we've seen these robots work, they don't vibrate. This doesn't make sense. And then we linearize the system and we look at the pole distributions, and we saw that some of the models have unstable poles. I was like, this doesn't make sense. Like, what is happening here? And if you are familiar with this type of things, you know that one way of fixing it is to add a linear wet friction. So you need a dissipative term. So our model was so theoretical that it was not dissipating energy. But friction actually dissipates energy. And then when you add friction, magically everything converges again because you're moving this unstable pole away. So that was one of the cool insights that we were like, what is the vibration happening? And it's because we didn't have a complete model. Obviously, this is not a physical number. And because our experimental setup is not running yet, we do not have good numbers. We have approximate-ish. But this is something that you need to get from data. So this is a data-driven approach where you need to know what are the values of the numbers in that matrix. But the theory says that, this is the reason why. Okay, so now that we have the model, the next step is what is the best way to go from point A to point B? So obviously, if you've taken Professor Kremanowski's class, you know about the brachistochrone problem. That was my main inspiration. It was like, yeah, you want to have, your intuition tells you, yeah, probably the straight line is the best path. But let me show you what actually is the best path. So we have a multi-objective optimization. So we want to minimize the force, which ultimately minimizes the energy that we spend because it's all about energy efficient. So the first term minimizes the energy. The second term penalizes the jerk of the state, which attempts to make trajectories more smooth, because you will see what happens if that goes away. So then obviously the constraints are the dynamics. So you have the dynamics, you have the bounds on the force in the cables. You also have path constraints, mainly for safety. The first constraint basically tells you that the panel has to be within the frame. Otherwise, it's not feasible. The second ones are more of realistic safety things. You don't want the panel to be super tilted. You don't want the panel to go super fast. Right now, we're limiting this movement to 20 centimeters per second. So it's a very slow movement. But we're talking also about very heavy panels. So you don't want to have a 2-ton panel moving around super fast, similar to the angular velocity. So very, very small velocities here. We don't want to have issues with that later. And the last part is you want to start stationary and finish stationary. So you have an initial position orientation, a final position and orientation. Usually the final orientation is 0 because you want to be plumb and level. And this equation here is a nice compact way of writing the dynamics whenever you have dt equals 0, basically. So you can write it in a nice compact linear way. And then you can come up to the optimal trajectory of moving from A to B, calculating the force and all of that, and arriving at a stationary condition. So what have we learned from here? So you have two coefficients, alpha and beta. If alpha is super low, basically you don't care about the control and you want to be your trajectory as smooth as possible, which this really approximates a straight line. So if you don't want bumps in your trajectory, just take a line and be done. But we really want to minimize the energy, right? So then we start cranking up that coefficient. So you can see now that this is more curvy, more like an S shape. We increase even more, and now you can see a little bit more of what this machine is doing. So it's picking up the panel here, and then it's rapidly trying to go back to the central axis. Because think about it, if you have the panel in the central axis, this becomes like a hoisting movement. You don't even really need forces in the lower cables because everything is on equilibrium and you just need to hoist with the 4 upper cables and bring it up and then drop it in the goal position. So that is what it's doing, but we still keep smoothness of the trajectory. So if we remove the smoothness, you can see a very sharp trajectory, but very clever. So what it's doing first is, in order to get to the central axis, is using gravity. So it's actually dropping the panel first, because you're minimizing the force. So you drop the panel to the central axis, and then you hoist up, and then this last movement is quite expensive, but it's short. So this entire trajectory really, really minimizes the energy that you spend, but as you can see, has quite sharp turns that might not be good from the vibration point of view. So we are not really using that, but this is a nice insight that we got from this trajectory optimization problem. Other thing that we learned is that, usually these panels they come in a truck and they are aligned all plumb and level. But if you pick the panel at a basically no orientation, plumb and level position, you have a very high initial force that you need because you're kind of like going from the corner of it and then trying to bring it back to the center. So you can even optimize the initial pickup orientation of the panel. So if the panel starts at a certain orientation, you can minimize the initial force and then minimize the overall energy that you use. You also get way nicer trajectories, as you can see in the linear and angular velocities. So that's another lesson of is not only optimizing the trajectory, but you can also optimize the initial condition of the panel in order to really, really minimize the force and the energy that the system uses. So then you can bring it from one corner to another in a nicely smooth way. Okay, so I just wanted to finish with current and upcoming research that we're working on right now. One of the main things, as I said before, is deep neural networks. How do we exploit them? There is so much talk about it. What can we do about it? So actually, during the last 9 months, we have spent a lot of time collecting data and labeling data. And right now, in the hackathon that we have, we were able to deploy this in Summit, in Frontier. Summit was the previous one. And you can see here the ground truth, which is points labeled as wall points, window points are here, and then there is a gutter here that is labeled as other, or also window sills as other. And this is the result of the deep neural network that we trained. So we're getting a little bit close-ish, not perfect, but we're still working on it. But it gives us at least interesting accuracy numbers here. So yeah, we have collected data of over 25 facades. We have over 100 examples of windows and doors, and we have a data set of over 50 gigabytes of only point clouds of building envelopes. We use the pointed plus architecture in case somebody knows about point cloud segmentation, which it has been quite widely used in different applications. And yeah, we're trying to improve this network and see if this can actually solve it. Because the nice thing about the network is that it's instantaneous. It's similar to when you're using ChatGPT and ChatGPT replies to you immediately. We want to do the same. You scan the building and you immediately get the dimensions that you need. We are trying to integrate all the different components in a single digital tool and try to have like an entire workflow of retrofitting buildings to optimize the entire process. And the last thing is that we are encroaching into new construction. So I took this picture yesterday from Liberty Street. I was walking there and I noticed that this building is being built with prefabricated components. So you can see here all of these kind of like rectangles. They are panels that are being shipped to the place. You can see the crane hoisting this panel, and then you can see the workers moving the panel, and they were doing like, yeah, just a little bit more, or talking with the walkie-talkie with the crane operator, and they were installing this panel in this part. So all of this, as you can see, could be relevant for even constructing new buildings. So with that, I'll leave it for questions, and thanks for the invitation.
From your slides, it shows that this technology is mostly for some specific shape of the building, like it's not very tall, and it's also like, yeah. So I'm thinking that what if this building would be very high? Like conservative, it's like 10 floors. So when you show the previous slide, I'm surprised it is your method, but oh, it's not. It's like the old method that used the workers to do it. So what if this technology used in this kind of high buildings? I'm thinking that maybe the robotic arm would be much longer, and it should be stronger, and the disturbance also would be stronger. Like there's a very strong wind, so which means that this control system should reject this strong disturbance. So, yeah. Will you consider, or did you consider this kind of thing, or this technology just for some low some just 3 or 4 floors building or something?
Yeah, that is a good question. Yeah, to be honest, right now we're prioritizing low-rise buildings, so 1 to 3 floors, because those are the most common multifamily or single-family buildings of the low-income housing part. So that right now has become the priority. These will be more for newer construction, and we cannot prioritize looking into this yet. But all that you mentioned is very true. The moment that the higher you go, the longer your cables are, more vibration, more disturbances, more problems. So hopefully we can get to tackle that later.
I'm also thinking, like, you can see that from this picture, this lift is strong, so we don't worry much about its safety with the helmet. But with that new technology, you just use some lines to lift that panel. I'm thinking, what if it falls down to the ground, and what happens that just a woman down happens to be there. Well, so maybe its safety should be considered more or be guaranteed
Mhm.
for the workers.
Yeah, no, safety is always forefront of everything. That's why we want to put bounds on how fast you move things, because it's a safety hazard too. You know, you're moving a panel very slowly, but it's a 2-ton panel, so it could do a lot of damage.
It might be out of the control.
Okay, that's okay. Yeah, Professor Scruggs.
Right, nice talk. So, my question is about your cable dynamics model.
Mhm.
Okay, so let me go back. Yeah, that's
This one.
right there.
Yeah.
Okay, so you have this nonlinear system model, expressed here as a first order system. And it looks like and I'm trying to get an idea for exactly how you're modeling the rigid body dynamics. So you have this capital phi, which includes your orientation angles, right?
Yeah, yeah.
So have you thought about doing this, just keeping track directly of the rotation matrix?
Yeah.
And doing simulation on a manifold rather than,
Mhm.
is there a reason why you didn't do it that way?
Yes, yes. The reason is that the rotation matrix is too expensive. It has 9 components, a 3x3 matrix. So that increases for no good reason your state space. There are 3 ways of solving this. One is using the rotation. I wrote the rotation matrix just because it's the nicest equation. It's like the one that I like. The second way is using quaternions. And the third way is using Euler angles. Rotation matrix, 9 dimensions, quaternions 4, Euler angles 3. So Euler angles give you the minimum realization of the system.
So I guess my reason for asking that is I wonder if you end up with different levels of problematicness regarding the damping issues that you're seeing. If you model things in terms of the rotation matrix directly, and rather than the rotation angles, we might see it either different or fewer issues related to the right matrix.
Well, honestly, we did all of this with all of the 3 formulations, and all of them gave us, those problems. Because the damping really, I mean, I wrote it as a matrix, but the damping is 0, 0, 1, 1, or coefficient here, coefficient here. It only affects these components. It doesn't affect these components. Yeah, but we did run all, because we were really trying to understand what was happening. So we simulated everything. They gave us the same results.
Questions about energy. You mentioned 70% upfront is through the envelope. Where's the other 30? Is this infiltration and equipment efficiency?
Good point. I honestly don't know. I don't do building energy modeling, so I don't know where the other 30 where the other 30 is wasted. But a lot of it is just heat that escapes.
The air infiltration, when people have to breathe fresh air, right? So there's, I think there's quite a bit there.
And
then in the later part of your talk, you're minimizing the energy of movement, right? Installation.
Yeah.
Do you have a feel for the magnitude of that problem that you're optimizing? Versus the result of, we got the facade now.
Yeah, the numbers that we have are the scaled down version, and numbers are
basically, does the installation optimization matter, right? Is the benefit so good for the facade, right? Or is it still a significant?
Well, I think it's not necessarily for the facade point of view, it's more for the component point of view. So you don't want to put the unnecessary stress on the mechanical component of the design.
Okay.
Because I didn't talk about it, but the winches to actually coil the cable, to wind up and wind down the cable, they are quite complex, because you cannot coil the cable on top of itself, because you need to keep track of the length of it. So you need to kind of like coil it on a helix. And then the bigger you are, you need another component to kind of like guide the cable into the helix. And you just want to really, you do not want to worry about that component, because if that breaks, the whole thing stops. You cannot coil the cable on top of itself.
Thank you.
on the back.
Yes, I had another energy related question.
Mhm.
Do you know or have a sense of, I guess, the energy savings from using this type of method just versus just the crane and walkie-talkie method?
No, yeah, this is all kind of like, we need to run the experiments. The main thing is that, yes, we want the energy savings and all, but the main thing is the time savings. And if you have an installation process with walkie-talkies, crews, and cranes, if everything goes well, is a good day. The problem is that things don't go well. And that is when this strategy could be really relevant, because you are installing panels, you made a mistake, you didn't realize you made a mistake, but you keep installing the panels. And at the end, you have a panel that doesn't fit. What do you do about it? You have to rework, you have to stop, first of all, you have to stop the whole thing. You have to still pay the crane. The crane costs you $2,000 per hour. You still have to pay for it. And you have to rework the panel. Nobody else is working because you cannot continue. So that is where the economical and time savings come from. The energy savings is the most for us to kind of like have a robust system and understand how the different optimal trajectories behave. But the best impact is, don't make mistakes, be accurate, and just have a plan installation. Mhm.
So on the note of time savings, if you wouldn't mind moving forward to trajectory optimization.
Yeah, let me see, maybe I can just exit. All right, how about this?
Yeah, so were you considering,
Mhm.
I guess, is the T sub T term, was that a fixed horizon length, or were you also trying to, I guess, do the minimum time problem?
Sure. Yeah, that's a great question. So we started with this one with a fixed horizon because it's simpler, I think. The next is to try to figure out the minimum time. So that is our next ambitious thing. So we haven't done it yet, but it is in the books. We're going to solve that. Yeah, I want to see how this looks like for the minimum time. Yeah, for sure.
So when you go from when you do the cable configuration selection, when you go from factorial of 8 to 4, what criteria you apply? How do you do this down selection?
Yeah, that is a great, yeah, I should have put that in the backup slides. But basically, what you do is you have your workspace, which is this entire area. So ideally, you want to cover the entire area with your robot because you want to retrofit everything here. In reality, you can't, because at some point in the corners, the force in the cable becomes too high that you saturate that force. You cannot, or you break it. So you cannot, get in the corners, for example, is very hard. So our criteria was to maximize the workspace, maximize the positions at which we can have full control authority over the robot. That was one. The other one is, even if you calculate those numbers, you could still have cable-to-cable collision or cable-to-panel collision. So you have to check those as well. So you have to make sure that the cable doesn't have some weird arrangement that if you try to pull them, they are going to tangle and then you cannot proceed. So that is another check that we had to go through. So we did check everything for getting into that 4 final candidates. But it's all of that is the process.
Oh, sorry.
No, one more question.
Actually, I have a lot of questions.
I mean, to be honest, we do have 5 more minutes. I think we can entertain a few more questions before we go party.
Yeah, sounds good. Yeah.
Okay, sure. So I guess firstly for this model, I wonder like if the dimension of the panel will be the something to like parameters or some issues considered in this model.
Yes. So that is a very important thing that we are going to tackle in this next phase. So the next phase is integrating all the different components and trying to optimize the whole process, the process as a whole, which includes sizing the panels. So, because you need to, let's say that you have a range of 3 different panels you can pick from. They have different dimensions. How many panels of which dimensions you pick, and then how you install those panels with the robot, And then based on those dimensions, how you optimize the robot trajectory or even the cable arrangement. So all of that is in the next step that we want to have it very customized because buildings in the US, all of them are very unique. So you have to have this level of customization. So we want to tackle the system optimization. And I have like a year to solve this. I don't know. We'll see what happens after 1 year.
It's a very cool problem. How expensive are the panels and what's the payback time?
I don't have the number. This is yeah, you are the second person that asked me this today, and I should my colleague Diana, she has the numbers because that is a very important thing, and the panels are economically sound. They are not crazy expensive.
Okay, but you're saving $300 a year.
Well, that is yes. That is once you finally finish the installation, then the potential is to save $270 for inefficient houses. Yeah.
That's a long payback time, isn't it? If your crane costs $2,000 an hour to install these.
Yes. So that goes to most of the touchy point of this, which is we do not have a lot of regulation for expediting this thing. Europe is very much ahead of us on regulation of, you need to retrofit, you need to be Energy Star or some sort of certification, or you cannot demolish historic buildings, you have to retrofit them. Here in the US, we're not quite there yet. There are some government incentives for doing it, but we are betting on the economics of scale of prefabrication. So we're hoping that because all of these panels can be prefabricated, then you have the economics of scale of that end that can offset this. But still, the question of how can you remove the cost burden from the homeowner, it's a tough one. Yeah, totally agree. Yeah. Wait, then yeah, you can go first. Yeah.
I had a follow-up to Professor's earlier question regarding cable collision checking. So is that a step you take after you generate the optimal control profile, or is that encoded as constraints, the optimal control profile?
For the optimal control is something we check after.
Okay.
Yeah, it's usually you can check cable to cable collisions using just the statics. You don't need dynamics. So because you can think that every point in space is in equilibrium, and then the math is easier. So you can check first and then solve the optimal control problem and then check again. We haven't encountered an issue where we solve this and then there is cable to cable collision.
Because what you get out then is you'll have a set of states for the panel, and then the cable positions because of that after you solve the problem. Thanks.
Yeah.
Got it.
All right, so I guess my last question is,
Yeah.
I see overall it's like an end-to-end automatic project. So I guess then from the beginning, it seems to me that measurement will be the most important thing here. So I see you use the point cloud thing, which have higher accuracy measurement.
Yeah.
So I wonder, firstly, why do you prefer? Is there any reason behind you choose the .NET or .NET++ for the segmentation? Because I know that before that there's something like feature extraction, and then just release some computer machine that can already efficiently extract the edge feature so that I can do a segmentation. So is there any reason behind it? Choose the neural network? And also another question is like, would that be an issue later on when it comes to control that there's some small error for the measure? How do you deal with that?
Yeah, good question. So the first part, we are right now, we started with .NET because it was the most popular that we found. So we didn't really have better candidates. And because it took us so much time to collect data and label, that we are really just starting understanding these deep neural networks. So we want to try more, and we do want to go for support vector machine type of approaches, more classical ML. We do want to do that. Now we have the team, because before it was only me. Now we have 2 more, so we can do it. And with respect to your second question, what was your?
How do you foresee some of the, let's say, measurement?
Oh yeah, the measurement error. Yeah. Honestly, at this point, we don't really have a good answer for it. So in the real-time evaluator problem, the next question we want to tackle is, okay, suppose that you make a mistake, either measuring or installing, but you know there is one. So you have to kind of like have a way to know that there is an error. And then how you adapt your future installation in order to mitigate that error. Suppose that you cannot correct it. You install it, the panel is installed, you made a mistake, but you don't want to correct it. How can you modify the rest of the installation to mitigate that? We're trying to explore that as well, because we understand that, right, there are so many things that could go wrong, how we can mitigate while you're installing. Yeah. Future work.
Oh, this is great. But how about there are probably many questions and you can talk to the speaker and let's thank you first.
Yeah.
Yes, if I was to ask another question, it's like, what did you do for your PhD?
I did internal combustion engines.
That's like very recently, I was celebrating like energy leakage.
Yeah, he was really nice to catch up. Yeah.
Smokers. It's kind of under, we have hundreds of this over time. Okay.
The email about like.
Last week, we had a meeting.
Really know you guys.
You are with Antonio.
Yeah, exactly, yeah.
Okay.
Yeah, it's, yeah, so.
Okay.
Also for that, I see, I can put it up. I was like, it's more really energy.
Yeah. A lot of good work and a lot of things we need help with. So.
Alright, nice to meet you.
Likewise.
Yeah, really good job with your design. Yeah.
Yeah.
I also have a similar feedback about the message.
Yeah. Yeah, likewise. Hey.
Thanks for that. I had a quick question. It has to be like, I think it's like the last mile thing. I was driving the car somewhere, and then there's the last mile thing. So it's like someone has to take the baggage and put it there. So like when you have your system and then you put it in the right orientation, then what happens? Like if you how do you like stick it? Right?
Yeah.
It's happening, but like I would say when you have the controllers, you have the motors, and then it's you're within the vicinity. So then you can't be within any orientation and then maybe press it so that doesn't stick out. When on the outside of the thing, it's just.
Construction has to have. Unless we turn over, we turn over.
A little bit. Yeah, you can get kind of look at the that is a very, very important question that we are still working on. So we have one person who is working on these kind of installations and how to do it, because right now really the idea is that somebody has to install these attachments on the existing wall, and then we come. But how are these connections designed, installed? How can they tolerate this type of automated machines? Yeah, we haven't figured that out. We have one person who's working on it, but it is a very relevant question, and I'm glad you didn't ask in front of everyone.
Amazing work. Thank you so much.
Awesome. Nice to meet you. Yeah.
Did you know I was included in the crazy idea?
He won't jump by himself unless he has other like crazy people. Qualified. Big adventures and smart. That's good. Okay. You talk to Andrea a lot?
I want to be very careful.
Okay.
Do you think it catch up with you?
No.
I wouldn't play with a lot of electric motors lately.
So, I was actually down in Oak Ridge.
I know he had some.
Couple months ago. I don't know, maybe it was even this year. We looked at, visited the rocks.
Yes.
And then all the great stuff that's going on.
Yeah. Quite cool.
We need to write it down.
That's we, I read the IEEE article that Barack was going on there and about demagnetizing motors, getting rid of materials, electric motors.
Okay.
And we actually are testing right now a BMW wound motor, which is, there's no magnets in it, and it has brushes in it to magnetize, use it as essentially an electromagnet in the motor.
Yeah.
Okay. And so in their IEEE article, there was a comment of, you can use brushes, but it's not gonna work for automotive applications. Inside road email for accident. We got a BMW motor that begs the difference, but it's never wrote me back.
So we have to make sure that it's good, but no, you have a good point there then.
Maybe
not
not
that
capabilities of the
So
system.
we've also been
We find something that's.
building up our process
You know,
for how you
this knows.
complete optimal control for these motors. So you bring it in and there's, I don't know if you know about field oriented control for electric motors. So it breaks it down from the rotating, the sinusoidal
We have.
control of the AC to a DC two-phase reference, right?
They declare it, they don't.
And so there's a fairly straightforward optimization process that you can go through, just linear constraint optimization problem
But I think.
for typical magnetic motors. But then with this wound rotor motor, you add in a field current, so you now have an extra degree of freedom. So we expanded our optimization, so the field current and all the voltage limitation and current limitation that come with it.
It's impressive. Okay. Are you publishing all of this?
We need to, we have not.
Okay.
We're not, we like publishing, but it's not the main priority, which is to run the market. But yeah, so that's what's going on.
Wow.
Too. And then we've got a few projects that are in the works. Just onboard discharging or.
But in addition to that,
So just use the
Well,
powertrain
how about
to dissipate energy without traction. application. So keeping the vehicle still, can you dump a bunch of energy through the motors to discharge your battery in case of emergency, in case of servicing, to evaluate the health of your battery, just some discharge profile.
Yeah.
Facilitate through.
Interesting. Yeah, I guess that's a good way of mitigating some of the issues with the batteries and just discharge it.
Yeah, so a lot of cool things.
Good stuff. Okay.
This stuff is very cool. And the fact that you get to build up the experimental system and actually go and implement your controls, that's the best part.
Yeah. Luckily, Oak Ridge is very good at saying, you know what, paper is not good enough. We have to do it. We have to show it. Like, okay, let's build it. It's stressful, but it's moving forward. It's tough getting done. Yeah. So, but it is nice. And then they say, yeah, let's do it. Let's make it happen. So we have all of that support and technicians and all of that.
Do you, I know that you had worked a little bit on the.
I don't think there's a way to, was it installation?
Yeah, installation infrastructure.
So you're doing any more of that?
Yeah. There is the current project I'm working on is called Target Anomaly Detection.
When I do that, it's
Which is you have the hydrogen nuclei coming at the mercury target. So then the nuclei hits the mercury gives off neutrons. That's the neutron source. But the mercury circulates on the target at a very high rate, 500 gallons per minute. It's just mercury just flowing the whole thing. And the nuclei are so energetic that it cavitates the mercury.
Really?
Yeah. And then they say, you know what? Let's just put some helium bubbles in the mercury to kind of like dampen the cavitation pressure waves. So they are basically patching a bunch of stuff with duct tape, and then they have anomalies. Say, oh, and then I don't know why this thing is suddenly breaking, and then the pressure rises. And I was like, okay, but the guy's like, but it works. Like, we don't want to touch it. It works, but we do want to identify whenever the anomaly comes, because this system has like 50 to 70 variables, and you have two people looking at all of these variables, and they say that on average, it takes them like from 2 hours to half a day to identify an anomaly. So if you can catch the anomaly sooner, you can do something about it, because you can always come back to a safer state, but then if you're like half a day and then the red button, the red light starts flashing, like what happened? So the idea is not to fix it, but to catch it earlier enough that you can do something about it. But yeah, that system is like, yeah, and then we're dumping the mercury here, and then we're maybe circulating at some point, but right now we're just dumping it. And they took me to the side where they disassemble the target because they have to change it every 6 months, and that costs $2 million every time. So they burn like $5 million every year just to keep the thing going. And there is just mercury all over. So of course, this thing is like protected with lead and a bunch of stuff. And you see all of that, that's mercury, radioactive mercury. So nobody's gonna get there inside in like 300 years, because that is just the last system. I'm like, oh my God, I know that this works. That's wild. So yeah, so I got to see some of the secrets of it. Of course, they show all of the nice stuff, but there's also a lot of things that, you know, it's kind of broken, it works, so they just keep on. But then it's like, how can we detect the anomaly early enough? Not fixing it, but just.
I'm gonna get all that ready.
So I'm getting into, yeah, a lot of
I already have it.
signal analysis processing. I understand.
I don't think.
Also some of it, there's a complex system.
But no, that should be,
Yeah, but that is the one I'm working.
maybe less than a day.
But it's all good.
Nice.
So
Required a speaker to take home all the extra 50.
all the cookies, I still need to grab one, so yeah, I grab a cookie.
The chocolate, I'm melting now. I get it.
Oh,
Oh, wow.
The chocolate chip was good. This one has some peanut butter,
okay.
but.
No, let me grab one of these.
I just wanted to stand around the mess.
All right. Thanks for showing me around.
Oh,
I have to take exercise. Likewise. Likewise.
Everything went well.
Everything went great.
I'm off to a nice, it's a nice night in Michigan.
Mhm.
Do whatever you get.
Yeah.
Well, Brian, it was nice to meet you.
Likewise.
Nice to meet you.
We
I'll,
will reach out to you next week about receipts for reimbursement for the car.
yeah, expenses.
Yeah.
Sounds good. Yeah, thank you very much.
Yeah.
I had a great time. See you guys. Yeah, love everything. Thank
Yeah,
you.
you too. Safe trip back.
Thank you.
Probably felt like it should have went out first.
Oh, that's okay.
Here.
Actually, my son did his training. And last October, we went to the Florida in Ohio. That makes sense.
Rather than the,
Cloudy.
you know, like they were paying so much attention about drafting
Yeah, then my wife's,
correctly.
trying to get into her wetsuit. She's so fit. I'm like,
By, you know, the Porsche case.
good thing is, so there's some delay. And that's not helpful immensely. Right? And so he gets in and then there's other people, he wants to go, looks in the water, it's like. When it's not right, you can't see as nice. And then the visibility is not great anyway, so he's like, we're like, come on, this is, you know. Okay, because you don't want to force it. So we went back, 3 weeks ago, my wife took him, I was somewhere else and they dove in a nice sunny day. Loved it.
Nice.
Next weekend, not tomorrow, but next weekend, we're doing his checkup apps. When he completes that, he'll actually have a certification to be able to do.
It's surprising how many just industry seems.
So, yeah, but my wife talks about,
It seems.
I thought, it's such a big Galapagos still.
Ah.
We do it then, but it's she's worried that that's pretty technical diving, it's complex. Because there's lots of currents and it's cold. Right up there. So I think she's worried that she's too old to do it now. But that's, I think of you when I think about if we're gonna go someday.
Hey, if you go, let me know. I'll hook you up with the best things.
How is the situation there? It's, is it deteriorated some? I saw some pictures.
No, it hasn't deteriorated, but it hasn't improved much. There is still some crime, you know, there is still this fight with the cartels and the coast is still best to avoid. So you're safe in the highlands. So I went on December actually to visit my family.
Wow.
But we were very much kind of like, we're going to visit family and that's it. And we had a blast, but
The coast is trouble, you said.
the coast is trouble, yeah, so avoid going to the coast. I don't know Galapagos is fine, but the coast is not good because
How do you get from Quito to Galapagos? You fly?
you fly.
Okay, so it's over the coast.
So you can arrive to the capital and then go to Galapagos. The capital is good. There's some issues, but the coast is really bad. It's kind of like, you know, Pablo Escobar in the 80s, like, yeah.
Not gonna do that.
So it hasn't deteriorated, but it hasn't improved that much. Some improvement, but not substantial. Yeah, I went there in December and now I don't know when I'm going back.
I have a wedding that I need to attend, so I won't be able to see the swimming and then,
Yeah, no,
picnicking and then.
everything good. Yeah, it's great. Outdoors cycling.
That's beautiful.
Yeah,
I was jealous that Joe got to come visit. I got close to you when we were in for spring break a year ago, and a half ago.
yeah, those
I thought I'd go to my office and pick up things and stuff, so
Okay.
that we can head out.
Yeah, I go with you then, I guess. Are you guys free? You coming today, tomorrow? There's a picnic or?
You mentioned it, I don't know the details.
Oh, that's right, yeah, you're not part of the group.
You're not in the meeting.
I'm working on the barn and building some cabinets. I'm still working on those.
Okay.
They look
So-
amazing. Now, we're going to Crooked Lake, I can send you the map,
That's tomorrow.
that's tomorrow.
Yeah, I probably won't be able to. Thank you. But-
Well, sometime you'll call us, you'll invite us in your place, that's what I want.
Will you come tonight? What do you mean? What I mean, I thought you were like. going here.
Really? Oh, yeah, we could have rice.
My wife will look at us and look, this is what we're doing.
Yeah, but you're gonna have to invite Brian and Emily because
You know Emily.
they stay with me.
Yeah.
They stay with me.
Yeah.
I took her, I rode home with her in the cab from the Comedy Cellar or whatever,
Yeah.
2 in the
We
morning.
went to the Comedy Cellar in New York City. And they went because we didn't realize that there were 2 cellars. So I went with another friend to one and then you went with Emily to another one.
And then when we got in, I got separated from her.
Oh, really?
And I ended up sitting in a corner in the middle of whatever it's called, the village or something.
Yeah.
Around a bunch of strangers and I get a drink. And then it was pretty cool, like most, I don't know, the people that we saw, most were like too harsh, like they were just like making fun of themselves and too much cussing. But then this black guy named Godfrey shows up and he's Nigerian. I don't know if you get to see him,
No.
but he does voices and accents, like he came out with German and then, I mean, just all across the board. And he was an unannounced, like he's a kind of a famous guy.
Exactly, like, okay, they can just walk in.
Yeah, and he did his little set, that was really cool. And then I didn't know that I'd seen any of you guys, and I'm outside, and there was Emily,
Yeah.
and I'm like, she was talking to the drummer or something, it was a guy from a band, and she was trying to get on stage, she was trying to work a deal to be able to get herself on stage.
That was her comedy day, so like, I wanna just get into the stage and do the
Yeah.
job.
And it's like 2 in the
Maybe
morning,
bad.
and I'm like,
Because she always jokes
we
about
gotta
it.
go, you know, I got this Uber, let's go.
Yeah.
And then that was it. So,
No, yeah, so yeah.
it's a good time.
Mhm.
I was,
Yeah, no,
I was just gonna take.
We could do a
I-
fire.
I was just gonna take them to live because they have good music today, I've heard. But then we're planning for some food,
Some food
maybe
at some point,
afterwards if we're not very tired. After dinner. I don't know. What do you want?
If you guys have a good plan, you go do your plan.
No, it's okay,
You wanna
I
do
mean,
a
we can
campfire?
change the plan.
You wanna do a campfire at my place? We can get a dog that'll jump on you, he's his buddy, his namesake. And he's Joe.
Joe.
He's Joey. We got Joey.
Joey,
Joe.
Joe.
So.
It's up to
It's,
you guys. I'd love to visit. It always happens that I have something with you.
We can do it. I know Emily would really like a campfire. Like you say fire and then she's in, so we could do it.
Let me check and see.
Yeah.
Check and see if you think you really want to. And then let me see too.
Yeah, you check too.
But I think
Yeah,
it's,
Otherwise, show up unannounced. Hello.
I'm the, hey, let's go have a party extrovert. And Jill's like, oh, wait a minute.
Yeah, I know, that's the thing. But I do need to exercise, otherwise I won't do well in my life. And today, and you don't like me around you when I haven't exercised for 2 days. So,
Hey, how are you?
Okay, yeah.
Oh, okay. Your phone is really, really quiet.
okay, let's keep talking.
Yeah.
I'm just leaving the lecture here. What do you think about having a campfire tonight and a little swan together?
Yeah.